Alright, so now we're going to finally get into calculating this integral numerically. So to make our lives a little bit easier, we're going to first of all start by restructuring the Duhamel integral just ever so slightly. So let's just sort of restate our equation here. So as I say, we're going to do a bit of restructuring here, and what we really want to do is we want to take this bit of the expression here and we're going to use a trigonometric identity just to expand it, because what we want to do is we're trying to separate out the t and the tau because we're integrating with respect to tau, and so we want to separate these terms out. And so it's this simple trigonometric expression to expand those. When we expand them, we end up with the following expression. All right, so basically we've turned this guy here into, expanded him into this guy here, right? So sine omega dt cos omega d tau minus cos omega dt sine omega d tau. Okay, so that was the expansion that we did. Now remember, we're integrating with respect to tau, right? So we want to isolate the terms that need to be integrated. So again, we're going to just slightly rearrange this equation. All right, so when we do that, right, we're going to end up with our expression u of t is going to be equal to a, right, a times e to the minus xi omega n t times the sine of omega dt minus b times e to the minus xi omega n t times the cosine of omega dt. Okay, right, so then we have a and b defined. So a was equal to 1 over m omega d times the integration between 0 and t of e to the xi omega n tau times f of tau times the cosine of omega d tau d tau. Okay, and b is the exact same expression except we swap out the cosine for a sine. All right, so what we've done here is we've basically separated out the terms, or isolated the terms that need to be integrated. So we're going to perform two numerical integrations, one to obtain a and one to obtain b. So that leads us on to the idea of the numerical integration itself, how we actually do the numerical integration. And this is actually going to be, if you've not done it before, this is going to be a lot easier than you probably imagine. That's one of the reasons I really like numerical integration. It's really very, very straightforward. So take, for example, right, in order for us to explain this numerical integration, take, for example, a, right? So consider a. Okay, so that's just some function that needs to be integrated, right? So just think about it that way. Just say, we're just taking a and we're just imagining it as some function, that's all it is, right? Just to make our lives a bit easier, we're just going to write it out this way, right? Some function of tau. Okay, so that's all we're dealing with here. So if it's a function of tau, we can plot that function of tau, right? So let's just do that. So we're going to imagine some function, okay, of tau, and remember, integration is just the area underneath that line, right? So if we have values of our function defined at regular intervals, let's imagine we do, well, we're basically trying to find the area underneath that function, right? So what we could do is we could say, well, we're going to approximate that area as a series of trapezoids, right? So a trapezoid is just going to be a straight line from there to there, straight line down here, straight line down here, and a straight line across here, right? So we have the area approximated, and the approximation comes about because, you know, between here and between here we actually have a curve, but we're approximating it with a straight line, right? So your approximation gets better and better the smaller the gaps between your samples, right? So we've got a series of trapezoids, and the trapezoidal rule of integration, numerical integration, is basically us coming along and calculating the area of one of these trapezoids, okay? And we're going to sum up all of those trapezoidal areas, and essentially that's the trapezoidal rule. It's a way of summing up, calculating all these areas and summing them all up. So if I was to consider this guy here, the area of that trapezoid, what would it be? Well, if I imagine that data point there is obtained as the value of the function at tau n, let's say, and we'll call this point here the value of the function obtained at tau n minus 1, well then the area of that individual trapezoid would be, and if we assume the gap between them is going to be d tau, well then the area would be the base times the average height, right? So the base is d tau times the average height is just f of tau n plus f of tau n minus 1 divided by 2. So that's the base times the average height is going to give me my area, okay? And then the total area under the function, which remember, that's all the integration is just the summation of each of those different trapezoids, the area of each of those trapezoids. So we'd say the total area between t equal to 0 and t equal to, let's say, tn, is going to be, the exact area is going to be the integration between t and tn of the function f of tau d tau, but we're approximating that by a summation using the trapezoidal rule, which is delta tau over 2 times the value of the function at tau 0 plus 2 times the value of the function at tau 1. And it's the same for all of the in-between values up until I get to 2 times the value of the function at tau n minus 1, and then the last value is only multiplied by 1, right? So plus the value of the function at tau n. And that essentially, that guy there, is the trapezoidal rule. The last time we came across the trapezoidal rule was, I think, in our beam deflection calculator project, where we were using the trapezoidal rule to do a numerical integration of the moment curvature relationship. So head back over to that project if you want to see me sort of explain it. Maybe I explain it a little bit slower than I did here. But basically, that's all we're going to do. We're going to come up with an algorithm, and we're going to write a function essentially that performs this operation, this numerical integration to calculate A, to calculate B, and then to evaluate this equation once we have A and B. And we're going to do that for every time step. We're going to step through the force time history, and we're going to essentially calculate the response of our system time step by time step using that numerical integration. All right, so let's jump over to our notebook now and actually do or build the code that does that integration for us. Okay, so we are now going to build some code or write some code that's going to perform this numerical integration and essentially solve the Duhamel integral numerically. Now, we're going to set up a situation where we've got some single degree of freedom system. The actual parameters of the system aren't really important for what we're trying to achieve here. And we're going to apply some forcing to it. Now, we're going to apply a harmonic force, and there's a reason we're going to apply a harmonic force specifically, because it's going to allow us in the next lecture to calculate the closed form solution for a harmonic force applied to a single degree of freedom system. And in that way, we're going to be able to validate our code. And that's going to be important. We always want to come up with some kind of validation exercise that allows us to test our code and make sure it's giving us the right answer. So that's why we're applying a harmonic force to our single degree of freedom system here. All right, so enough said. Let's just crack on with this thing here. So the first thing I'm going to do, I'm going to just define my system parameters, my single degree of freedom system parameters, right? So I'll just imagine it's some mass of 1,000. Again, completely arbitrary values. We'll say xi is going to be 5%. We'll say the natural frequency of the system, again, arbitrary. Let's just go for 1.5 hertz. That sets the angular natural frequency as being 2 pi f. So that's going to be 2 times math dot pi times f. Let me see. Omega d, the damped natural frequency, the damped WD, is going to be equal to omega n times math dot sqrt. So it's the damped natural frequency is the natural frequency times the square root of 1 minus xi squared. Again, we cover that in the fundamentals of structural dynamics course. So I'm going to want xi squared. And we'll just put some notes in here as we progress. All right, so, let me see. I haven't run, I got to run this cell first to import math, and then we can run this. Okay, excellent. So now we can go ahead and set up our force, right? Now, before we set up the force itself, or the forcing function, I'm going to set up a time vector, right? So I'm going to say the maximum simulation time here is going to be 20 seconds. and we'll say again, now I think, did we use a 1/10 of a second last time? This time we'll say del t is going to be equal to a 100th of a second. And we'll say then that means the time vector is going to be constructed using np.arange, starts at 0, goes up to t max plus del t, and it goes up in steps of del t. Okay, that's my time vector. Now we've got to define the force that gets applied to this single degree of freedom system. So we'll say the forcing frequency, I'll just say F sub force is going to be 1 hertz. That would set up omega f. The angular forcing frequency is going to be 2 pi times 1. The amplitude of loading is going to be 100 newtons, and that would mean that the force itself is going to be P times np dot sine. Again, we're feeding in a series of numbers, a series of time values rather than a single value. That's why we're using numpy dot sine instead of math dot sine, and that's going to be the forcing frequency omega f times the time. Okay, that is our force vector setup. Now we're ready to do the sort of the bulk of the work here, and that is the Duhamel integral calculation itself. Okay, now the way we're going to do this is we're going to want to package our code in such a way that we can take this code and reuse it, right? Reuse it easily without having to rewrite it every time. So the way to do this is to basically define a function, okay, and write all of our code within that function. Then we can call that function from different locations within our code, and it will execute, you know, all the code in the function, right? So let's go ahead and define a function. We're going to call it Duhamel. Call it whatever you like. I'm calling it Duhamel. It's going to take in 2 parameters, right? 2 arguments. The first one's going to be a time vector, which we're just going to represent as t, and the next one's going to be the force vector that we're going to represent as f, right? So this Duhamel, and then you've got to close off your function definition with a colon like that. Okay, now all of the code we write in here is going to get called every time we call this function. All right, great. You'll notice that we're not passing in like the natural frequency of the system or the mass of the system or anything like that. So we're gonna call, whenever we call this function, we're relying on the fact that a whole series of other parameters are already or have already been globally defined. If you want a truly encapsulated function that you can literally copy and paste out of this notebook and bring somewhere else, you would have to explicitly pass in the other parameters that this function needs. But this function is going to be only called inside of this notebook where these parameters are already globally defined. So that's why I'm only passing in the time vector and the force vector. Okay, let's see, where to next? Well, the function itself is going to output a series of displacement values, right? So I'm going to start by defining essentially a container, right? A container of values, or a container that's going to hold all my displacement values. Now I'm going to initialize all of the displacements for every time step to 0, and then as we progress through, as we loop through the time vector and the force vector, we're going to override those zeros with the actual displacement values, but we're going to start off by making them all 0, right? So I'm going to say u is going to be np zeros len of t. All right, all that's doing, and let's close that bracket off, all that's doing is it's defining a whole list of zeros, and the length of that list of zeros, the number of elements, is going to be the length of the time vector. So it just basically gives us a 0 for every time step. Now let me see the next thing. In fact, let me write some notes here as I go. Okay, so next I'm going to define initial values for a variable I'm going to call a cumulative underscore I. I'm going to set that equal to 0 starting off, right? And then I'm going to say b cumulative I is also equal to 0. Okay, now I won't say much more about those 2 numbers until we get a bit more code written, and then I'll circle back and explain these in a bit more detail. But for now, I'm just going to say that I'm initializing values for the cumulative sum used to calculate A and B at each time step. Remember, we're calculating values of A and B at each time step. And in order to do that, we're going to have to sum up the value, or sum up the area of the trapezoids, all of the trapezoids that led up to that current time step. So we're going to have to keep track of some cumulative sum, right, in order to calculate A and in order to calculate B at every time step. And so I'm just initializing a very first value for that cumulative sum being equal to 0 and 0 for A and B. So again, this will make more sense as we, the more code we write, the more sense it's going to make. So now we're at a position where we can cycle through the time vector and evaluate the response at each point in time. And so actually what I might do, before I write any more code, what I might actually do is drop in a cell here, change it to a markdown cell, and just drop in the equations, because it's going to be handy for us to reference these equations potentially as we're going through this, right? So I'm now going to write a for loop where we cycle through the time vector and evaluate the response at each time point. Okay, right, so for t in t, right, so remember large, t is the time vector that got passed into the function, and we're cycling through each of the values, right? So close that off with a colon. Now I also want an iterator, a little counter that goes up from 0 every time I loop through this for loop, right? So I'll say for I, that's going to be the counter, in, and if I want a counter, I need to enumerate t. With this for loop, every time we go through, we're calculating the area of one of these trapezoids. Now, I can't calculate the area of a trapezoid if I only have one value, if I'm on my first iteration, right? I need two values. I need the value on the left-hand side of the trapezoid and the value on the right-hand side of the trapezoid. So I'm going to write a little test here that is only going to execute the code inside if we have a value of I that is greater than 0. Because the first time I come through this loop, I is going to be equal to 0. I can't calculate an area the first time I go through, so I can only calculate an area if I have at least two values, okay? And in other words, if I is greater than 0. So now we're actually ready to calculate A for the current iteration. So that's going to be essentially this equation here, right? Equation 2 here. So what do we need to do? We need to calculate the value. We need to calculate this value here, okay, for the current iteration, and we need to calculate its value for the previous iteration, okay? So we're going to define yi, just a variable, yi. Now that's going to be this expression here, evaluated at the current time step, right? The current value of t. So it's going to be math.e to the power of xi times omega n times the current time. Now the current time is ti, right? So remember, t was passed in, we're looping through t, and I want the current value of t, which was t, at index I, because remember, I counts up by 1 every time we go through the loop. Now I could have had, because this is also the current value of time within the loop or within the iteration of this for loop, I could have also done t. And that'll be the very same thing, but I don't want to do that because I want to stay consistent, because I can't access the previous time by using t, right? In order to access the time, the last time we went through the loop, I would need to use t I minus 1, and because I want my equations to look consistent, I'm going to use ti here. Okay, so that's the exponential. That's this exponential part dealt with, times the current value of the force, right? So I'm going to look into the force vector and extract the value at I for the current time step, times math.cosine. I can use the cosine from the math library now because I'm only passing in a single value of time. So I'm going to have omega d times t at the current time step. Right, so that's the value of y for the current time step, or the value of this, this function for the current time step. Now I want the value at the previous time step. All right, so that's going to be y, we'll call it I minus 1. So that's going to be the exact same, except I'm indexing into the previous time, the previous force, and the previous time. That's why I could only come in and evaluate this expression if there was a previous time and a previous force. And that's what this check here makes sure, that there was a previous one. Okay, so now that I've got that, I can calculate the area of the trapezoid, right? So let's define that as area, right? So area underscore I is going to be equal to, again, we saw this, right? This is just the trapezoidal rule, 0.5 times del t, globally defined, times the yi I just calculated, added to y I minus 1. So that's the area of the trapezoid. Now remember, I want the cumulative area. I want the area of all trapezoids up to this point. Okay, and so what I'm going to say now is, and that's why I initialize this at 0, right? So the cumulative area, A cumulative I, is going to equal, let me see, I'm going to add on to whatever it was previously, right? So it's going to be whatever it was previously, which was A cumulative I plus the area that we just calculated, right? The area we just calculated. Now I can do shorthand for that, and I can just say A cumulative I plus equal to area, okay? And that just adds, let me bring this up here. That just adds AI onto whatever the previous value of that was. And so every time we come through this loop, we're adding a new amount of area onto this here. Okay. So now that we've got that done, okay, we've taken account of the additional area for the current iteration. We can go ahead and calculate the value of A, right? Because A cumulative I, that there is essentially everything to the right of where my cursor is now. That's us evaluating the integral between 0 and t of that function. But don't forget, to actually get the value of A, we got to multiply by 1 over m omega d, and that's what we're doing now. So we're going to say AI is equal to 1 over m times omega d times A cumulative I. Why do I keep doing 1? It's I. Okay, so let's put in some notes here just so that it's kind of clear what we've done. Now we got to basically repeat the exact same thing, but just do it for B, right? So we'll say calculate B for the current time step. And essentially, let me see, I can copy down pretty much all of this. The only thing that changes is this needs to be sine, and this needs to be sine. Now, if I missed anything else, I think that's all okay. Obviously, we're dealing with B now, so that can be B. This can be B. Change our note to say B, and that should be it. So now we've calculated the correct value of A and B for the current time step, and now all we got to do is evaluate this expression here to work out what is the actual displacement at the current time step. Okay, so make sure you're still within your loop. So we'll say calculate the response. All right, so that's going to be U. Now this is where we're overriding a value of 0 essentially. So we'll say UI is equal to, and all we're doing is writing out this equation 1 here. Okay, excellent. That should be it, right? So that is our Duhamel integral function, okay? That's just us looping through the time vector, essentially, time and force vector. And for every time step, calculating the current value of A and the current value of B, both of which require us to keep account of a cumulative sum, okay, of this and this. So we've calculated A and B for each time step, and every time we calculate a new value of A and B, we come along and we also calculate the response for that current time step. And the thing you can't forget to do at the very end is return out of the bottom of this function. So let me see, step back out, we want to be in the function, so the last thing we do is return U, okay, the response. So whenever we call this function, it will execute all of this code on whatever value of time vector and force vector we pass in, and it will return out the response for our system. And again, let me emphasize, we're relying on the fact that things like xi and omega n have been defined globally, right? And so our function knows what those values are. Right, let's, let me see, shift enter. Okay, right, what have I done wrong here? Right, so we've got some syntax error. What do we think that is? Okay, it's saying return U is a problem. Let me see, why is that a problem? I bet you it's a typo in here somewhere. Well, I don't know if this is the problem, but I've spotted one issue. That should be I instead of 1. Now that's not likely to be the problem. Let's try again. Now that wasn't the problem. That would have given us a different problem. Okay, well, I've spotted another issue. There should be a closing bracket here. All right, so let me just break this up and make it a bit easier to read. Right, so I have AI times e to the power of all of that times sine of that times b, or minus b times e to the power of all of that times cosine of that. Let me see, does that fix it? That fixes it. Okay, right, so I had a missing bracket basically here. Right, so now we've defined our function. we just got to go ahead and call our function, right? So let's call this thing, right? So we'll say, we'll call the function Duhamel. We got to pass it in a time vector. Well, that was defined as time, and our force vector was defined as force. And we want to assign the output. Remember, our function gives us back u. We want to assign that to something. So we'll assign that to a variable we're just going to call response. Let's run that. Okay, so we run it. Doesn't seem to have kicked back any errors. Now we can plot that response. All right, so plotting is going to be the usual plotting code. We'll define a figure, add a set of axes, and then plot onto that set of axes. So now we've defined a set of axes. We can say axes.plot. And what do I want to plot? I want to plot time versus the response that I calculated. Let's see what we get. So that's what we get. Let's tidy it up a little bit. It looks right, but let's tidy it up. Usual housekeeping. You've seen me write this code, so I'm just going to paste it in. Adding an x-axis label, y label, title, setting my limits to 0 and t max. Okay, excellent. So there we have it. So that's the response of our system. Now, if we look at that, that's exactly what we would expect to see, because we've taken a single degree of freedom system and we've applied a harmonic load to that system. And again, if you're familiar with the sort of study of dynamics, fundamentals of dynamics, you'll know that when you apply a harmonic load, you can essentially break the response of your system down into two components. A transient component, which essentially decays away, it dies away, and then a steady state component, which is what's left after the transient dies away. And you can see that's what we've got here. We've got some transient behavior at the start here when our system is getting going, but that dissipates and our system stabilizes to the steady state, right? This is the steady state of our system. So that looks right. Okay, so our next task, which we'll tackle in the next lecture, is just testing to make sure this is right, because we have an equation that can give us this response, okay? And we're going to just focus on the steady state response. But we've got an equation. So I can plot an equation, compare it to what our numerical solution gave us, and they should be perfectly aligned. They should be lying perfectly on top of each other. So we're going to see that in the next lecture.